Thank you very much. First, I would like to thank the organizers to invite me here and give me the opportunity to present my work in this nice environment. I really enjoy staying here. Since I guess the audience is a mix of physicists and mathematicians, so I choose a topic, one of my work related to the instanton modular spaces, which I believe is some good topic which has a lot of interaction between mathematicians and physicists. So this work is based on the work with me and my collaborators Ali Pomoni and Xingyu Zhang, this past two works. And on the other hand, so just 1 day after our second paper was out, so there is another paper that written by two mathematicians, Fasola and Manavari. They basically gave a geometrical or mathematical rigorous definition of our tetrahedron instantons. And also, well, we completely didn't know that our two groups are working on the same thing. And we actually posed some conjecture on the instanton partition function in our second paper, and just 1 day after they proved it. so this is kind of like the fastest time when mathematicians prove a physics conjecture, as far as I know. Okay. So I will first explain what do I mean by tetrahedron instantons. First, let me give you some motivation. So we know that the modular spaces are very interesting topics in mathematics, and many Japanese mathematicians, including some of the audience sitting here, have important works on this topic. And a lot of these modular spaces can also be realized by different brane configurations. And if in the from brane side, what we can do is counting BPS states. And also a lot of Japanese physicists are working on this side of the story. And by counting the BPS states, interestingly, many of these countings are related to the different invariants for the modular spaces. So let me give you some example. One novel example is the ADHM construction of the instanton modular spaces, and these are closely related to the D0, D4 brane systems. And another example will be consider the Hilbert scheme of endpoints on C3. And this modular space has a close relation with the brane system of ND0 brane probing 1D6 branes. Okay, and in that case, one can match that the instanton partition function here is the same as the Donaldson-Thomas invariants. Okay. And then it's also a very difficult question, and many people are working on it. Is consider the Hilbert scheme of endpoints on C4. And so I know recently there are a lot of works on this side, understanding the modular spaces, and I also know that several Japanese mathematicians are working on this. And also from the physics side, this is related to the magnificent 4 model. Which is a brane system of D0, D8, and anti-D8 branes. Okay. So our motivation is trying to build something in between. So you see there's a gap from between the C3 and the C4, right? So what we are trying to do is trying to find something that leaves some brane configuration which lives in C4, but on the other hand, it's just a bunch of union or intersection of D6 branes. So it's some 3-dimensional singular variety, but lives in the C4. So it's a sort of interpolating situation between the Hilbert scheme of endpoints on C3 and the Hilbert scheme of endpoints on C4. And you will see from our results, indeed, is interpolating between these two. So, okay. Any questions so far? Also, if you have any questions or if anything that I said is not clear to you, please feel free to stop me and ask questions. So here is what we call tetrahedron instantons. It's a brane system where we have k D0 branes probing intersecting D6 branes. Okay. Let me also, I already draw the brane system plot here. So let me show you. So since we are working in the 10-dimensional string theory, so we start with the direction x0 to x9. And for simplicity, I group the x1, x2 direction to a complex plane, which I call C1, and then similarly C2, C3, C4. So I have a four complex plane, which will be the C4 there, where all the D6 brane lives. Okay, then I start with the k number of D0 brane, which supported only on the x0 direction. And x0 direction will be my time direction here. And then I start with D6 brane, and this D6 brane will also support it on the time direction, but the remaining 3 space dimension can be supported on any three of these 4 Cs. So I will label them accordingly. For example, this I will have n 1, 2, 3, which I called 1, 2, 3 brane. This will be supported. So this 1, 2, 3 D6 brane will be supported on the time direction and C1, C2, C3. And then 1, 2, 4 D6 brane will support it on the C1, C2, and C4. So dashed line means the branes are supported on this direction. And dot just means the brane appear as a point in this direction. So because this D6 branes lives in this C4, so I can have 4 different sets of D6 branes. They are intersecting with each other, but each of them occupies or supported on the 3 different dimension, 3 different direction in the C4. So in the end, I'm getting something So in the end, I'm getting some singular variety, which is a union of C, 1, 2. Let me write it there. C, 1, 2, 3, 3. Union C, 1, 2, 4. Union C, 1, 3, 4. Union C, 2, 3, 4. So this will be a subvariety in C4. So this is then I will study some modular space, which is some generalization of Hilbert scheme of endpoints over this singular variety. But it's three-dimensional, but it's slightly more complicated than C3. But it's not quite C4. So we can actually avoid some problem when computing modular space of C4. And as you probably saw already, I already had a lot of different notations. So I have to spend some time setting up a notation of labeling all these different branes. So I call this 4 underline. This set is the index set of 1, 2, 3, 4. And this 4 check set. This 4 check set is the set of 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. And so this they have elements and different labels. Say, for example, if I have A check, which means I'm subtracting this A indices from the 1, 2, 3, 4 set. So this A check is an element in the 4 check set. Okay. So then this capital A is some element in the with the indices 1, 2, 3, 1, 2, 4 like this. So for example, when I write this C3A, it means the tensor of 3 different C's, different complex planes. Like C1, 2, 3 means it's a C1 times C2 times C3. And I write this n vector, summarizing the number of the number of different D6 branes. So in the end, it can be summarized in one of the tetrahedrons, so that each face of the tetrahedron representing one set of the D6 branes. And I will show immediately what does this each vertices means. Okay, so this is actually the origin of our name for the tetrahedron, because the index set of and the configuration is best described by a tetrahedron. But there is a funny explanation for the name tetrahedron comes from. Is if you look at this singular variety, this is what I heard, that this is the central fiber of a toric degeneration, where the associated polyhedron complex is a tetrahedron. So you can also think that is as an origin of the name. But we really invented this name just to for easy labeling all the different D6 branes. Okay. So okay, so this is a brane setup of our system. Any questions? Okay, now we want to study the modular space for this brane setup, just like similar in the ADHM case or other cases. However, we would also like the system to have supersymmetry, so that we can do some exact computation. If we go naively for this brane configuration, no supersymmetry can be preserved. Therefore, one has to turn on the Navier-Schwarz B field to preserve supersymmetry. So, to preserve SUSY, we have to turn on non-trivial B field. which is a two form, look like this. And so if I introduce another parameter, e to the 2 pi I nu a, is to replace the field strength of a BA. We can compute that when this parameter nu a equals to 1/6 plus r over 3 for all a, there are two supercharges are preserved. So that means the remaining low energy effective model will have at least two supersymmetry. And you can see that by looking at each tetrahedron, so each face of the tetrahedron representing one of the D6 springs. And then each node of the tetrahedron actually are related to this component of the B field. And the nodes which oppositing each node, each face, they are related by some relation. So with this setup, we can write down the low energy effective model. Well, it is a model, so just following the correct notation yesterday. So this is described by some 0-2 supersymmetric quantum mechanics. Which are described by this quiver. Oh, sorry. No, there's no such line. Okay. So each dashed arrow corresponds to some Fermi multiply. And each solid arrow corresponds to some chiral multiply. So let me explain briefly how does this come from. So each of the D6 spring gives a certain flavor symmetry to this low energy effective model. And this rank of the flavor symmetry is the same as a number of each D6 spring. And then the KD0 brane will contribute to some gauge nodes in the middle, which if we have a KD0 brane, we will have a UK gauge nodes in the middle. And then since I'm looking at the low energy effective model, so the strings stretching between the D0 brane and D6 brane will be effectively some particles in this model. And in this case, the strings between D0 and D6 brane contribute to a chiral multiplet and a Fermi multiplet. Then I need also consider the strings stretching between the D0 branes. And this also related to the B field there. So in the end, we got a physics model. And we can also write down the superpotential for this model. So because it's a bit too complicated, I won't write it down. But roughly, it's if I call this, if I label this 4 and 3, 1, 2. It's the basic idea is each matter multiplet coming from a 1d6 brane are coupled with the self-adjoint one with the opposite number. So this 1, 2, 3, this 1, 2, 3 multiplet are coupled with the B4 here. So we cannot arbitrarily write down the coupling constant. For example, there will not be any coupling between the 1, 2, 3, and 2. Okay. So any questions? And then we define the instanton modular space of tetrahedron instanton as the modular space of this low energy effective model, which can be written as a quiver representation with a relation. So the quiver representation is really similar to this thing. So the modular space, by just trying to find the configuration which has a minimal lowest energy, is described by this quiver with a relation. Okay. And each line we have, this is I, 1, 2, 3, I, 1, 2, 4. So each A, remember that this capital A is an element in this index set. So each IA is an element in the home C. CNA to CK. Well, I mean, I would like to think this as some NA times K complex matrices, and each BA It's just a home ck. Okay. And the relation is taking the this potential V to be 0, which can be written here. So because this V is a square of 3 different terms, and each term is greater or equal to 0. So the total V equals to 0 imposes 3 relations, and each of them has to be 0. Actually, let me write it here, because I'm going to use it. So in the end, the moduli space can be redefined like this. So it's a BA, IA, subjecting to the relation V equal to 0, and up to gauge transformation, which can also be written as some pre-image of some certain moment map. And quotient by UK. Sorry. And these moment maps are So if you are familiar with instanton moduli spaces like spiked instanton or the ADHM instanton, you will see this our definition of the moduli space is just some generalization of this. Okay, so for example, the instanton moduli space that Hiraku started before was look like this, right? It's the Jordan quiver. So what we have here is just adding more self-adjoint loops and more framing. But just remember that you cannot combine all these framing nodes together, because each framing has its own relation with the self-adjoint loops. So you can view this as a generalization. So our moduli space is a generalization of the of a ADHM moduli space. Okay. So this is the modular space that we obtained from brane setup and low energy effective model. Let me give you an example. Let me just just write down the mathematical definitions that are copied from that two mathematicians. So they claim their work is they claim that this modular space so geometrically, so this is a work of Fasola and Manavari. They claim this our modular space, tetrahedron instanton modular space, is the following code scheme. Where delta is just what I wrote before, the singular variety, where all the D6 springs are supported on. So it's a subvariety of C4. And this epsilon n is the torsion shift on delta. It's a pullback of the structure shift on the each C3. Sorry. This is a push forward, right? Yeah, this should be push forward. So this is a torsion shift on delta, and this iota is an inclusion map from the C3 to our singular variety delta. Okay. So these mathematicians claim that this code scheme is the same, describe the same modular spaces that we obtained from brane setup, and it has a very interesting property that the virtual dimension of this modular space is 0. However, the structure itself is still complicated. Okay, so let me give you some example. The simplest case is when this n is 1, 0, 0, 0, and you still have KD0 brane. So this goes back to KD0 brane probing 1 D6 brane, right? So then the modular space reduced to the modular space of a Hilbert scheme of K points on C3. Then the second example is starting from the definition of our this definition of our tetrahedron modular space, and you drop the last equation. You drop the equation, the condition theta equal to 0. Then, without this, the last condition, we obtain the Hilbert scheme of K point of C4. So indeed, our modular space is sort of like interpolating between these two different cases. There is one more example when this n vector is nm0, 0. So I only include two different set of D6 springs which are intersecting with each other, and let's take k equals 1. So we have one D0 brane probing like two different sets of perpendicular D6 springs. Then in this case, the modular space can be written as at least as a set is the same as C2 times C star times C Pn minus 1 union C star times C Pm minus 1, then union C Pn plus m minus 1. So so this C2 coming from when you don't have D6 springs on the last two components, you have a freedom. So basically, from the equation you have some freedom on the B fields. Two B fields can be taken completely free. So this C2 comes from here, and this component. This component roughly describes the situation where all the D6 springs on one direction are stacked, are just stacked at the same place, and the other D6 spring on the other direction, they are separated, and you are sort of like counting the distance between the D0 branes with all the distance between D0 branes and all the D6 branes. So in this case, roughly the C star counting the D0 brane between this stack of D6 branes, and the Cpn minus 1 counting the distance between D0 and this perpendicular D6 branes. And this case is similar, where this set of D6 branes are stacked with each other, and the other set is separated, and we have D6 branes probing the distance. And in the last component is all the branes are separated. So this is a schematic configuration, explains the configuration. However, I have one remark. So last setup has a very interesting description. So if we consider this modular space, so it describes the modular space of the Jordan quiver, right? I dagger and B dagger, right? So I can define two different actions. So one is a T1 action, which acts on Bi, sends Bi to some Q times Bi, and where Q is just a complex number which is not zero. And the second action is sends Bi to Bi times H, where H is a diagonal matrix with n plus 1 and m minus 1. So we observe that this n m 0 0 1. So this is a remark. This modular space is same as C2 times is V. So the fixed component of this V modular space under T1, and then union with the fixed component of Vn plus M1 T2. So in this case, it seems somehow related to the modular space described by the Jordan quiver, and you can also work out that it's actually this relation works when for the arbitrary instanton number case. So this relation is somehow this special relation is what we found in this special case when we have only two different sets of D6 branes. I'm not sure if this is just a coincidence or there are more profound reasons behind that. So I guess actually it's a great opportunity for me to actually pose the questions to the mathematicians here. So whether this is a coincidence or it means something. Okay. So any questions? Yes?
I have a question about the logic. So we start from brane configuration. The configuration is basically a point in time. So for example, a parameter space. And then the low energy effective theory of that configuration gives us a gauge theory. And then we continue the vacuum.
Right.
So by vanishing the scalar in the vacuum of that space of that theory. So this is basically saying that the parameter space of the brane configuration is equal to the vacuum of that space, right?
Yes. Yeah.
May I know why?
Right. So you see, roughly, what we have is some schematically. What we have is something like this, right? And then we are so the vacuum expectation value, which parameterize my modular space, are something like some vacuum expectation value coming from the strings, right? A string stretching between the D6 and D0 brane. And in some loose sense, you can just view this as a distance, like classical. If you use a classical approximation, this is roughly the labeling the distance between the D0 and D6 brane. Some sort of, I mean, classically it's some sort of distance, but of course, I mean, you have quantum corrections. It's not quite. Okay, so to better understanding the invariants of this modular space. So one quantity we can compute from physics side is the instanton partition functions, which since I already gave you the low energy effective model, we can compute it as some supersymmetric partition function. So roughly for this configuration, we have SU4 times this symmetry acting on our low energy effective model, and let T be the maximum torus of our symmetry group, and I will introduce its QA and TAA will be the equivariant parameter corresponding to the maximal torus. Then we compute the instanton partition function can be written as as a sum of all instantons. And this parameter p basically counts how many instantons we will have, and then the supersymmetric partition function for this for the particular configuration of n vector and k. So the exact formula for this partition function is too complicated to write down, but just remember that once I gave this n vector and k, I can draw this quiver theory for the supersymmetric quantum mechanics. Then this roughly this z can be written as some integral over some contribution of chiros and Fermis and vector modules. And the fact that the virtual dimension of this modular space is 0 can reflected in this integrand. So this integrand is a product of some theta function or rational function or geometric trigonometry function, depends on which kind of partition function you are looking at. But the number of theta functions in the numerator and the number of theta functions in the denominators are the same, which reflects the fact that the virtual dimension is 0. And localization computation turns this this integral into a sum over some 3D partitions. And contribution from chiral, Fermi, and vector. And also, by the work of mathematicians, they claim what we computed as the instanton partition function is some T equivalent Euler character for the some virtual structure sheaf. Okay, so I'm really glad that in this case, all the formula I wrote down has a rigorous mathematical definition. So this leads to our main result for the partition function. So which is our conjecture, which is proved 1 day later. So it's remember it's the partition function. The total partition function depends only on the n vector. Because I already sum over k. It can be written as a plasticity exponential of this actually very simple form. So here, this x bracket means x to the half minus x to the minus half. And delta n is a shorthanded notation for the Q1 n 1 check, Q2 n 2 check, Q3 n 3 check, Q4 n 4 check. And the plasticity exponential is defined like this. So the interesting thing about this final result, final partition function, is that although I'm computing the equivalent Euler character with respect to the maximal torus of the whole SU4 and this UN, I have 4 UNs here coming from 4 framing nodes. So in principle, there's no way to way that the final to expect that the final relation are not dependent, are independent of the equivalent parameter for the framing nodes. But actually, for this Euler characteristic, if you sum over all the instantons, the results only depends on the equivalent parameter for the SU4, and now depends on the equivalent parameter for the framing from the framing. So you see that our final result depends only on Q, and now depends on T. This property is something called rigidity, which well, I mean, this is some term from mathematics which I'm not understand properly, but this is some mysterious result, at least from a point of view of from physics.
So, do you know how to prove that formula? At least what the strategy or line of argument?
So the way that they prove their formula, there are at least as far as I know, there's 2 technical steps.
Okay.
So the one step is actually prove this thing doesn't depend on T. It's using the rigidity. I think we have an actual expert in the audience, and the other part is some technical difficulty relating that something about this minus sign here. So something that this minus sign actually doesn't matter.
And that leads to the resistive form?
Yes, so it leads to that. But I guess the important part is proof this doesn't depend on T.
What about how did you find the formula? By trial and error?
Yeah, by trial and error. I mean, computing from 1, 1, 0, 0, and then like slowly increasing the order and a bit guesswork. Yeah, so, okay. Since I have only 5 minutes left. Right, again, we can take some limit of our instanton partition function. One is n0, 0, 0, right? As a consistent check. So actually, we reproduce our formula reproduce generalized Donaldson-Thomas invariant C3. And I also mentioned that our configuration is somehow related to the magnificent 4 model. So actually, we found that our instanton partition function is the same as a magnificent 4 partition function at some specialized value. So in the magnificent 4 model, their partition function has a parameter s, which is a relative position between the D8 and the anti-D8. So from their result, we just plug in this to some special value. We can get our result. So this is a hint that our configuration can be understand as some some annihilation between D8 and anti-D8 configuration in the magnificent 4 model. And in the end, we can also take the cohomology limit, a cohomological limit, which is parameterizing each qi to as e to the beta epsilon a, and taking the limit beta goes to 0, and keep epsilon a and p fixed. So this is going from since this basically means from this configuration, I compactified on the further on the along the x0 direction. Okay. So in the end, the cohomology limit, in physics sense, is compactified further on the circle. It's written as, can be written as some product of a magma Hom function. Where this RA is minus is this combination. Okay. But on the other hand, actually, this magma Hom function already appear in the when you're computing a topological string partition function on C3. So what we have is in this limit is cohomology limit of our brane configuration is the same as the product of the total topological string partition function of NA. So this can be understood as some generalization of Donaldson. So this is a generalization of this DT Gromov-Witten correspondence. Okay, so this is going down one dimension. So one can still starting from this this configuration and going up. So from 1 dimension to 2 dimension, which I have to change this to D1 brane and D7 branes, so that they can also occupy the x9 direction. Then the resulting, I'm getting a 2-dimensional low energy effective model with 0,2 symmetry. And if I compute the supersymmetric partition function for this 2-dimensional series, I get the elliptical generalization of the instanton partition I wrote before. But for this elliptic instanton partition function, the final result will depend on the this equivariant t parameter of framing. So there's no rigidity for the elliptical ones. Okay, since my time is up, so I guess it's a good time to wrap it up. So today I introduced to you this modular space that we obtained from some brane construction, which we try to interpolating between C3 and 3-dimension and 4-dimension. And actually, so there are some questions we would like to further explore. So one question is, all these partition functions can also be realized as correlators of some free chiral bosons. So it would be, so this is somehow a hint of there might be some other symmetry acting on the maybe some bigger symmetry acting on the cohomology of the modular spaces. So it would be nice to actually find the relation between between this and Masahito had this work on the quiver Yangians, and I'm not sure if we can apply your technique to our configuration. There are some discussion on the cohomology Hall algebra on the spiked instantons. So our modular spaces also looks like a generalization to the spiked instantons. So we would also like to study whether there can be coha action on that thing. I guess I hope this arouse your interest in studying this modular space. Okay, that's all. Thank you very much. Yes.
So what happens if you replace D6 brane with D4 branes? So you have 4 D6 brane, but you can replace D6 with D4 brane inside 6.
So you mean replace all the D6 branes to D4 branes? I believe you get, if you have intersecting D4 branes, you get this configuration spiked, which they call spiked instantons. Yeah, but it's also an interesting question if you replace some of the D6 brane to D4 brane, so getting D0, D4, D6 brane configuration. But this is also an interesting question, but we haven't computed yet. But maybe Marichu can say something about that.
Well, we had this approach via the exponential networks that may be applicable in this case. But it's hard to implement D6 on that complex.
Okay. Yeah, Nikita also had this global 4G network, which.
Global 4G network, yeah, that's a recent one.
Yes, also.
I think that should give you more on the spot that configuration, like very general. But these are also on C4.
Right,
kind
right,
of, yeah.
right. It's in principle, using his framework, you can discuss something like D0, D4, D6, D8 system, right?
That's right. Yeah. Yeah, that case maybe. Yeah.
Yeah. So I guess if you combine D0, D4, D6, it's also very interesting, but it's not done yet. Yeah. Thank you very much for the question.